Hello, how are you? ازيكم عاملين ايه؟ يا رب تكونوا كويسين. Can we weigh one atom? No, we cannot. It's very tiny. Okay. Can we weigh a handful of atoms? المرة دي, this time, yes, we can weigh a handful of atoms. طيب, let's imagine that I have 100 rice grain. The weight is 2.5 grams for the 100 rice grain. So what is the weight of one rice grain? What do you think? Yes, if 100 rice grains weighed 2.5 grams, then the weight of one only would be 2.5 divided 100. That's 0.025 grams per 1 grain of rice only. So I divided the total mass by the number of grains. If an atom is very tiny and we cannot weigh one atom, so what we will do? We will do exactly what we did with the rice. We will do the weight of many atoms at one time. Remember what we did? We weighed a handful of rice, 100 rice grains, and divide its weight 2.5 grams per their count. So we'll do the same for atoms. Weigh many of atoms at the same time, then the atoms is going to behave like rice grains. I'll just have to divide the mass of the bunch of atoms that I'm gonna weigh, divide by their count. It will give me the mass of one atom, correct? Yes, because here 2.5 over 100, and here mass over count also of atoms. Now we have a little bit strange question. I have two balloons, and these two balloons have the same size. Do you think that they will contain the same amount of air? Like the air particles count inside is the same? Yes. If they have the same volume, they will have the same content of air. But what if I change it and asked you a different question? If I have two balloons, this time one of them contains oxygen and the other one contains hydrogen gas, and the volumes are equal. Do you think they will still contain the same number of particles inside? Yes. Even if the gases are different, as long as they are in the same conditions, if they have the same volume, the number of particles inside is the same. So if you counted the particles of this gas and the particles of the oxygen gas, then they will have the same count. So what is the name of this principle? The name of this principle is Avogadro's law. Avogadro has found out that if I have any two gases which have the same volume and the same conditions, the number of particles in these gases will be the same. So if I have 22.4 liters of hydrogen gas and 22.4 liters of oxygen gas, this is basically the same volume, and they are at the same temperature and at the same pressure. So both are at the same conditions. Are they going to have the same number of molecules of the gas inside? Yes. How did you know that? With the Avogadro's law. Let's revise this again. Two balloons, same size, one with hydrogen, one with oxygen. Do they both hold the same number of particles? Yes, they do, according to Avogadro's law. But if the hydrogen balloon and oxygen balloon both hold the same number of particles, do they have the same volume? Yes, mister, this is the same thing, but you are talking it backward. It still applies. Now one more question. different one this time. If both balloons have the same number of particles inside as they have the same volume, which one is heavier, hydrogen or oxygen? Now, this is not Avogadro's law. We already know that they have the same volume and number of particles now, but the mass will not be the same. The mass of oxygen and hydrogen will be different. In this case, I have to say that the oxygen is going to be heavier. The oxygen is going to be heavier because its molecules are heavier than the molecules of hydrogen gas. Actually, the volume tells us the count and the number of particles. And the volume of gas is a little bit different from its mass. You see, the volume of any gas actually is not dependent on the particles too much. The particles are very, very tiny compared to the actual gas volume. So they don't make any difference. Even if the particles are a little bit bigger compared to the container, it's not. So the volume of the container basically is empty. So even if the particles are a little bit bigger, it doesn't make any difference. That's why if the particles count is the same, then they are going to have the same volume, but the masses is different. Because if we put the particles on a balance, theoretically, then they weigh more. So the oxygen gas particles are much heavier than the hydrogen gas particles. They are both diatomic for sure. So we agreed. Do they have the same count? Yes, they have the same count. Do you have the same volume? Yes, they have the same volume. Do they have the same masses? No, they don't have the same weight or mass because the particles of the oxygen is much heavier than the particles of the hydrogen. So, if we want to weigh the atoms and molecules, can we weigh them in grams? No, they are too small to be weighed in grams. So is the hydrogen atom super tiny in mass? Yes, the hydrogen atom is very, very tiny, and actually all atoms are very tiny in mass. Approximately, what is its mass? About 0.000000000000167 grams. Can you see? If you are able to see it and put it on your scale, then is the scale going to move? No. It will stay zero here. Of course, you're not going to see it or put it. Imaginary, if you are putting it, the hydrogen atom will weigh nothing. It's very, very tiny. So I don't need this big scale that we are using. I need another tiny scale that will be imaginary scale that's used to measure our atoms. So it's a relative scale. In this scale, chemists invented a new unit to make the weighing easier. What is the name of this unit? It's called the atomic mass unit. This is a comparative unit. Let's say that you are a child and you don't know anything about kilograms and grams. So you'll go with your friends and say, look, I'm gonna weigh everything with the stones. So this is a stone, and my toy is as big as one stone. What if I have two toys? Then they will be big as two stones. And then you keep weighing everything relative. So when you get a little bit having a bigger toy, you will say, oh, this is a very heavy toy. It weighs almost 100 stones. So stone is your reference. This is the reference unit which you are using if you are playing with the stones. And here I do the same. Atomic mass unit, this is my reference unit. So everything I will see its weight compared to one atomic mass unit. But what is equal to one atomic mass unit? So pick something from these three that you imagine will have the same mass as this reference unit that we have invented together. Is it the carbon atom? Is it the hydrogen atom? Is it the oxygen atom? Yeah, I know all of you knew that. One hydrogen atom has a mass which is equal to one atomic mass units. So it's equal to the reference stone that we have used, and then everything else I will weigh reference to this. So if I want to see what is the mass of oxygen, I'm gonna see how many times the oxygen mass is big compared to the hydrogen. How many times the oxygen atom is big compared to the hydrogen. So I will see that the oxygen is almost 16 times as big as the hydrogen atom, I'm sorry, and the carbon is like 6 times as big as the hydrogen. So I don't care now what is the meaning of 1 or 16 or 6. I just know that this is a comparison with the smallest unit. So the smallest unit is the 1 AMU equivalent to 1 hydrogen atom, while the oxygen atom will have a mass that's equal to 16 times the mass of the hydrogen. So that's equal to 16 AMU. And the carbon atom will weigh 6 times the mass of hydrogen. That's equal, one carbon atom equal to 6 AMU. So simply you are comparing how many times this particle or any particle is heavier compared to the hydrogen atom as a reference unit. That's just a shortcut that will help us to compare these particles which have very small size without using this 0.0001. If one hydrogen atom is equal to 1 AMU, does it mean one atom of hydrogen weighs 1 gram? No. Remember, we had two scales. The normal scales that we are using every day, and we said that we cannot use this for the atoms. It's very tiny. And the tiny scale that we have made up by comparing everything to the hydrogen atom, that's using AMU scale. So this is the gram scale. Each one you will use to weigh an atom, I will use this one because one atom of hydrogen will be equivalent to 1 AMU on this scale. This is my unit. I cannot put it here. If I put this hydrogen atom on this scale, remember 0.0000, all these zeros that we had, and then 167 at the end. So I'm going to put the atom here to measure it. And if I have a carbon atom, I will also compare it against this hydrogen. So I will say that the carbon atom is 6 times the hydrogen atom, and the oxygen is 16 times, and so on. But that did not solve my problem. In everyday chemistry, I'm not using that micro scale. I'm only using this scale that's available. So you think that I cannot use it? I can use it, but I can use it only if instead of one atom, I'm gonna bring a big bunch of atoms. So if I take a huge group of atoms, like a mole instead of one atom, what is that, a mole? It means that I'm gonna get a very big number. So how much is this number? Is it 1,000, 1 million, 1 trillion? No, actually, it has to be more. Why it has to be more that? Even 1 trillion, it will not be enough. All these atoms are not going to be enough. Yes, because finally, if you put them, then it's not going to change also. It will be still zero. It will be too light to weigh on my scale. So I have now not one atom, I have millions of atoms, millions and millions and millions of atoms. What do you think I can use it for? I will still try to put it on the scale, it will fail. Only when I put a very big number, this number is called 6.022 times 10 to the power of 23. How many zeros are there? Is this a small or big number? It's a very big number. Why did you have to put all this big number? Because when you get this big count of atoms, only the scale can finally see it. Which scale you are talking about? Our scale? Yes, we are going to finally be able to use our everyday scale, the gram scale, to measure that. But remember, that's not the AMU scale. That's the big scale that we are using every day. But how, mister? You said you are not able to use it. Yeah, I'm not measuring one atom now. I'm measuring that big number of atoms. So what is the count again? This is a very big count. Instead of saying this number every time, I will just say Avogadro's number. What is Avogadro's number? This is that very big number of atoms that when you put them together, finally, you can see them and you can weigh them. And finally, the numbers on the scale are going to move. So if you bring this big number of atoms, of hydrogen atoms on the scale, then you are going to see a mass finally. And it's not going to be in AMU. This is our everyday scale. We use the grams only. That's abbreviated as G unit. So I had to bring all these atoms together to be able to finally see it on my everyday scale. If I brought one or two or million or trillion or anything less than that, most probably I won't be able to see it for sure on my, and I'll have to, my scale, and I'll have to go back to my tiny scale, imaginary one, that will be suitable for people that are very tiny, like that use, or even tinier. So let's answer the question finally. What if we take a huge group of atoms like mole instead of atoms that will be finally measurable on our scale? So how many atoms are in a mole? 6.022 times 10 to the power of 23 atoms. What is this word mole? Yeah, instead of saying Avogadro number of atoms, Avogadro number 6.02 times 10 to the power of 23 every time, I'm gonna say mole. This is a secret word between me and you. All of us chemists only know that word. Because normal people know something like a pair. If you brought a normal person who is not a chemist and ask him what is the meaning of a pair of atoms, he will say two. You told him what is the meaning of a dozen of apples, he's gonna tell you, I will have 12 apples. So everybody knows how big is a pair or how big is a dozen, but nobody except us know how big is a mole. It is 6.02 times 10 to the power to 2 times 10 to the power of 23. Is it an apple or egg or what? Of everything. So it was just a count. This is a very big number. So it just means a very big number of atoms, of apples, of books, of anything that you need to imagine. So if one hydrogen atom is equal to 1 AMU, I use this the tiny balance, the tiny imaginary balance equal to one hydrogen atom only, 1 AMU. Don't forget our relative unit. Then 1 mole of hydrogen atom. Oh, this is the normal balance. I can use it now. Big, yeah, compared to the tiny balance. This one, I can put only 1 mole of hydrogen atoms to be able to see it. Remember, that's too big. That's a very big count. And then I can finally see a mass. The mass will be 1 gram this time, not 1 AMU. So if we compare the same, but 1 atom of oxygen and 1 mole of oxygen, that's only 1 atom measures 16 AMU on our tiny balance, 16 times heavier than the hydrogen atom. While if I'm talking about a big number of hydrogen atoms, to be able to measure it on the scale, I will need this time 1 mole. That's 6.022 times 10 to the power of 23. Remember, out of zeros. This time the mass will be 16. Did you notice that the number is the same? 16 here and 16 here, 1 here and 1 here. The only difference is the unit. Here AMU, here grams for 1 atom. And for a mole of atoms, that is just 1 atom here. But here 1 mole of atoms, that's big count. And here 1 atom and here 1 mole of oxygen atoms still. Thank you. If you have been paying attention today, you have learned today that we cannot weigh one atom, but we can weigh many. Equal volumes of gases hold the same number of particles. Atoms have different weights, so gases with the same number of particles can still have different masses. Chemists use AMUs and the mole to make these numbers simple. And finally, I have one win for you. We now can count the uncountable atoms just like counting rice grains.